Welcome, everyone. Today we're diving into the professional's playbook for AKS lifecycle management. Keeping up with the rapid pace of Kubernetes releases can be a significant challenge for any organization. This session is designed as a strategic guide to help you master the upgrade process. We will focus on how to navigate these updates to ensure your environment maintains peak stability and security, all while increasing your team's deployment velocity. Let's explore how to turn routine cluster maintenance into a streamlined, predictable part of your operational workflow. To achieve the best balance of stability and compliance for your production clusters, we recommend adopting the N-1 minor version lag strategy. Essentially, this means staying one version behind the latest release. For example, once AKS releases version 1.34, your goal should be to plan and execute your upgrade to version 1.33. There are three critical reasons why this is our recommended approach. First, it maximizes stability. By avoiding the bleeding edge, you bypass any initial platform-specific defects or day zero bugs that might surface in the first few weeks of a brand new release. Second, it ensures perpetual compliance. This strategy keeps your environment safely within the standard 12-month AKS support window, providing your team with a comfortable 8-month operational buffer. Finally, it is a technical necessity. AKS policies prohibit skipping minor versions during an upgrade. For instance, a jump from 1.32 directly to 1.34 is blocked. By maintaining the N-1 lag, you ensure your upgrade path remains clear and supported. To understand our upgrade strategy, we need to look at what we call the upgrade clock. As you can see in the top row, the Kubernetes upstream community releases approximately 3 minor versions per year. Azure Kubernetes Service follows this cadence, typically reaching general availability a few months after the upstream release. The critical piece to track here is the AKS support lifecycle. Each minor version has a 12-month support window. If we try to stay on the absolute bleeding edge, we're constantly chasing the next release. Instead, we recommend an N-1 adoption strategy. For example, if we wait to upgrade to version 1.33 until 1.34 hits general availability, we immediately give ourselves a comfortable 8-month support buffer. By intentionally staying one version behind the latest release, we can move away from reactive, high-pressure scrambles and transition into a cycle of planned, predictable maintenance. Moving into Phase 1, our primary focus is de-risking the upgrade. Statistically, the #1 cause of upgrade failure is the presence of deprecated APIs that introduce breaking changes. To understand the risk, we need to look at the Kubernetes API deprecation policy. For beta APIs, those like V1 Beta 1, there is a strict 3 minor release window. Once an API is marked as deprecated, you have 2 subsequent releases to migrate. By the 3rd release, that API is removed entirely. If you haven't migrated your workloads by then, the upgrade will fail. Stable APIs are more resilient and won't be removed within a major version, but migration is still eventually required to access new features. To mitigate this, AKS provides a proactive defense mechanism. 12 hours before a scheduled upgrade, AKS automatically initiates a validation check. If the system detects any deprecated API usage that would lead to a failure, it will proactively block the operation. This is a critical safety net that prevents control plane failures before they happen. The bottom line is that a reactive approach is insufficient. Proactive detection is a mandatory pre-upgrade gate for maintaining a healthy environment. To maintain a stable environment, we use a 2-pronged strategic blueprint for identifying and eradicating deprecated APIs. First, we focus on static analysis, or code at rest. The goal here is to scan all Kubernetes manifests, Helm charts, and infrastructure as code repositories before they are deployed, requests that introduce deprecated APIs at the source. Second, we employ dynamic analysis to catch runtime calls. This is crucial for identifying calls made by controllers, scripts, or external tools that static analysis might miss. We recommend querying Azure activity logs within the Microsoft.Container Service namespace to track live usage. As shown in the code snippet, you can target specific API versions to see if they are still active. This is especially vital for managing AKS preview APIs, which typically have a short 1-year lifespan. By combining these 2 methods, we achieve comprehensive coverage and ensure total API compliance across our infrastructure. Let's dive into the migration from endpoints to endpoint slices, a pivotal change in Kubernetes version 1.33. Conceptually, we are seeing the official deprecation of the legacy v1/endpoints API in favor of the discovery.k8s.io/v1/endpoint slices API. This isn't just a naming change, it's a necessary evolution for performance and scale. Endpoint slices provide the overhead capacity needed for services with hundreds of endpoints and offer native support for modern features like dual-stack networking, capabilities the old API lacks. This shift will directly impact anyone managing custom controllers, service meshes, or monitoring tools that query service endpoints directly. If we look at the technical visual, you can see the structural difference. Previously, a single monolithic endpoints object held every IP. In the new model, those are broken into multiple slices linked by a label selector. To successfully migrate, there are three primary technical requirements. Number 1, shift from name to label. Instead of fetching a single object by name, you must now use a label selector, specifically kubernetes.io/servicename, to aggregate all relevant endpoint slice objects. Number 2, handle multiple slices. Your logic must be prepared for a single service to have multiple slices. This is standard for dual-stack networking or for services that scale beyond 100 endpoints. Number 3, adopt the new readiness structure. Readiness is no longer tracked in separate not-ready addresses arrays. It is now a per-endpoint condition, meaning you'll check a Boolean ready flag for each individual address. Adopting to these requirements now will ensure your infrastructure remains performant and compatible as the Kubernetes ecosystem moves forward. Now that we've moved into the execution phase, it's time to fine-tune the upgrade engine. Think of these as your control dials for balancing speed, safety, and cost. First, we have max surge. This dial controls how many extra buffer nodes are created during the upgrade. Increasing this value speeds up the process, but keep in mind it temporarily increases costs and requires more subscription quota. For production environments, we recommend a setting of 33%. Next is drain timeout. This sets the maximum duration the system waits for pods to gracefully evict before a node is re-imaged. While the default is 30 minutes, you'll want to increase this for stateful workloads or any applications with long shutdown procedures to ensure you don't lose data. Finally, we have the node soak duration. This is an intentional pause after a node is upgraded before the engine moves to the next one. While the default is 0, we recommend a 5 to 10 minute soak in production. This allows your monitoring systems to validate the health of the new node, significantly reducing the blast radius of a potential failure. Next, let's talk about what we call the upgrade killer, misconfigured pod disruption budgets, or PDBs. The problem arises because the node drain process is designed to strictly honor your PDB settings. If a PDB is configured too strictly, for instance, setting max unavailable to 0 for a single replica deployment, the node drain will wait indefinitely to evict that pod. This stalls the process and can bring your entire cluster upgrade to a halt. To prevent this, we have a two-part mandate before starting any upgrade. First, you must validate all PDBs to ensure max unavailable is set to allow at least one pod eviction at a time. Second, if a service requires high availability, you should scale up that deployment before the upgrade begins. This ensures your availability needs are met while still allowing the nodes to drain. Finally, there is a break glass contingency, the enable force upgrade flag. This should be used with extreme caution. It bypasses PDBs entirely, which can lead to service disruptions or complete downtime. It is strictly an emergency measure and never a substitute for correct PDB configuration. Now let's dive into what is widely considered the gold standard for achieving zero downtime, blue-green deployments. The process follows a simple 4-step workflow. We start with our active blue cluster running the current version of our application. To upgrade, step 1 is to provision an identical green cluster. In step 2, we deploy the new version and validate it thoroughly in this isolated environment while production traffic continues to flow to blue. Once we are confident in the new release, step 3 is the traffic switch. We update our traffic manager, or DNS, to instantly route users to the green cluster. The key advantage here is risk mitigation. Because the blue environment remains live and untouched, we have an instantaneous rollback path if any issues arise after the switch. Finally, once the new environment is confirmed stable, we decommission the old blue cluster to save resources. This strategy is best suited for mission-critical, high-availability workloads where any potential disruption from a standard in-place upgrade is unacceptable. Moving into Phase 3, we focus on continuous maintenance. Our core strategy here is to decouple Kubernetes version upgrades from Node OS security updates. By managing these as two separate tracks of change, we can isolate issues and significantly improve cluster stability. Track 1 covers major Kubernetes version upgrades. These are planned lifecycle events that occur approximately every 4 months, following an N-1 strategy. These upgrades re-image your nodes with new Kubernetes components and are controlled through the cluster auto upgrade channel. Track 2 addresses Node OS security updates. These are much more frequent, occurring daily or weekly to handle security patches and minor bug fixes. Depending on the update, this may involve a full re-image or live patching. Our strategic recommendation is to manage these two tracks using separate planned maintenance windows. By dedicating a minimum 4-hour window to each, we ensure that changes are isolated, making it much easier to maintain a stable, secure environment. When creating a node pool in AKS, the OS SKU you select determines how major operating system upgrades are handled. You essentially have two paths: default SKUs or versioned SKUs. Option 1 uses default SKUs, like simply Ubuntu or Azure Linux. This is designed as an easy, no-touch experience. When you perform a Kubernetes version upgrade, AKS automatically moves the OS to the latest recommended major version. For example, transitioning you from Ubuntu 22.04 to 24.04. This is the best choice for teams that want to stay current with minimal manual intervention. Option 2 introduces versioned SKUs, such as Ubuntu 22.04 or Azure Linux 3. This provides increased control because the major OS version is pinned. It will not change during a Kubernetes upgrade unless you manually update the SKU yourself. This is ideal for safely testing new OS versions in a dev environment before a full rollout, or for providing a clear rollback path if a newer OS version causes issues. It also allows you to maintain LTS stability for your OS even if you are moving through different Kubernetes versions. As shown in the example at the bottom, you can manually update a node pool to a specific versioned SKU at any time using the Azure CLI. Moving into Phase 4, we need to focus on contingency and validation. The core principle here is the fix-forward imperative. It is critical to understand that AKS does not support minor version rollbacks. Attempting to downgrade, for example, from 1.33 back to 1.32, is not a supported operation and can lead to severe compatibility issues. Because we cannot simply roll back, we recommend two paths forward. First, address and retry. If an in-place upgrade fails, troubleshoot the specific blocker, such as a quota limit or a pod disruption budget, resolve it, and then retry the upgrade operation. Second, recreate and migrate. In the event of a catastrophic failure, the strategy is to spin up a new, stable cluster on the previous supported version and restore your workloads from backups onto that new cluster. Ultimately, the best contingency plan is prevention. Thorough pre-upgrade testing in staging environments remains our best defense against failures in production. Once the upgrade is complete, we enter the critical phase of post-upgrade validation to ensure the cluster is healthy and stable. We focus on 4 immediate health checks. First, we verify component versions. By running kubectl get nodes, we confirm that the control plane and all node pools have successfully transitioned to the target Kubernetes version and the latest node images. Second, we check the health of the control plane. We need to ensure that core components, such as the API server and scheduler, are fully operational and communicating without issues. Third, we look at workload stability. This involves checking application logs for unexpected errors, monitoring response times, and confirming that all services remain available to end users. Finally, we perform a deep dive into the API server logs. We are specifically looking for any lingering warnings regarding deprecated API usage to guarantee that all migrations were successful and that the environment is fully compliant with the new version. Moving on to the AKS Lifecycle Management Framework, we view this not as a one-time event, but as a continuous discipline. It starts with strategy. To balance stability with staying current, we recommend adopting an N-1 versioning policy and deciding early on your OS SKU model, whether you'll use the default settings or opt for specific versioned images. Next is preparation. This is your pre-flight check, where you proactively detect and remediate deprecated APIs. It's also the time to thoroughly validate your pod disruption budgets and run full tests in a staging environment to catch issues before they hit production. Then we move to execution. Here you have fine-grained control. You can tune upgrade parameters like max surge and soak time to manage the pace of the rollout, or utilize blue-green deployments for your most critical zero downtime workloads. Finally, we enter maintenance and validation. We suggest managing Kubernetes and OS updates on separate tracks to isolate variables. Once an update is complete, perform rigorous health checks and approach any contingencies with a fix-forward mindset to maintain momentum. By mastering this cycle, you transform cluster upgrades from a reactive chore into a strategic advantage, ensuring your platform remains stable, secure, and ready for whatever comes next.